Hello everybody, this is the second video for Chapter 9 of the Reinforcement Learning course. So in Chapter 9 we're introducing value function approximation where we use a parametric function to approximate the value function. And the reason why we do that is because for very large state space problems, the typical tabular approach where we list separately the estimated value for all the states won't work. Okay, so you cannot store, if you have 10 to the power 10 states, it's impossible to store all of them. And of course, updating all of them would be even more complicated and longer. So this wouldn't be feasible. So instead of having separate estimates for the value of each state, what we can do is we can have a parametric function which approximates the current estimate of the value function. And then instead of learning the value of each state separately, we will learn the best parameters of the function, which shall give the best estimate. So in the previous lecture, we've introduced the objective function we will try to optimize when searching for the optimal set of parameters, sorry again. So this objective function was defined as, well, it was denoted VE bar here, W. So this is what the objective function we're trying to optimize when we optimize the vector of parameters. And this objective function, it's the mean square error between the true value function and the approximate value function from our parametric approximation. And the mean square error is weighted by the distribution mu, which we define as the on-policy distribution, which represented the long-term percentage of time spent in each respective state. So just one recall here, for this chapter we're working only on the prediction problem. We're not refining the policy, but we keep the policy fixed and want to calculate the state value function associated with this policy. And we use on-policy methods instead of off-policy, which means that our current estimate of the optimal policy is the one that is used to generate episodes. Okay, so this is a quick recall of what we discussed last time. So now we have our objective function, but how do we minimize it? Okay, so in the next lecture, what we will do is we will discuss gradient methods or stochastic gradient methods that can be used for such purposes. So we will illustrate, like we just said, how to use stochastic gradient descent, or SGD, for finding the best approximation of the value function in our framework. So one quick note, stochastic gradient descents, they're extensively used in practice. It's most likely the most popular approach that is used by people to optimize policies or value functions estimates in reinforcement learning. Okay, so they're very well suited to learn incrementally while experiencing the environment. So stochastic gradient descents, they're very good to learn a little bit at a time every time new information comes in. So we will describe how to apply this procedure in our prediction setup with approximation. Okay, so here we will consider the column vector W, which is the weights or the parameters of the value function. Okay, and we're going to assume it's d-dimensional, where d is typically much smaller than the number of states, so as to achieve dimension reduction in our problem. Okay, so it's easier to optimize d parameter where d is quite small in comparison to optimizing v by s for all the states s. So here the parameter vector w, since its values will vary through time, then we shall denote wt being the current value of parameters after time step t. And one assumption that we will make, we will assume that the value function estimate is differentiable with respect to all components of W. Okay, so our function with parametric function which approximates the value function, we assume it can be differentiated with respect to all parameters. Okay, so this allows us to use gradient methods. Okay, if approximations aren't differentiable, then we cannot compute its gradient, and we cannot, of course, apply stochastic gradient methods. Okay, so we shall now illustrate how that stochastic gradient descent approach works in our framework. We will start with a simplifying assumption that is unrealistic, but let's assume that it is the case for now, and then we'll see how to circumvent problems associated with this approach. Okay, so let's assume for now that on each time step we observe the state st and the value function associated with this state. Okay, so this is true, we always observe the state, but the value function, we don't know it in practice. This is what we're trying to estimate, so it's impossible that we know this quantity exactly. Okay, so in practice we'll use approximations, but for now let's assume we know this, we observe this quantity on every time step. So furthermore, let's get we're gonna assume that the states in our sequence appear with the same frequency than indicated by mu. Okay, so mu is the long-term percentage of time spent in each state. So here, if you just, for example, generated episodes in the conventional way, this would work, because of course, if you just generate episodes normally, the percentage of time spent in each state would be the stationary distribution for continuing tasks, or the average time spent in each state for an episodic task. Okay, so you can simulate the states normally through episodes, and this will work. There are other ways to simulate them, but let's not discuss that. Okay, but the important is that the frequency with which each state is simulated matches the distribution mu. But if you do that just as we did before, episode by episode, this should work. So we will want to use this information, so st and v pi st, on every time step to update parameters wt so as to try to minimize our objective function, which is the mean square error between our approximation and the true value function. So if we apply the regular gradient descent, so this was already discussed in previous chapters, but if we apply regular gradient descent, then this would entail having a sequence of parameter estimates as follows. So the next estimate is the current estimate minus 1/2 times the learning rate times the gradient of the objective function. Okay, so this is the objective function. Now, why minus 1/2? The minus is because we're trying to minimize. If we tried to maximize, it would be a plus sign, but since we're trying to minimize, we go in the opposite direction of the gradient of the objective function. And here the 1/2, well, this constant can be absorbed in the alpha, so it doesn't matter whether we put it or not. But because there are, like, when we'll differentiate squares here, there's the power 2 which will go in front and cancel out with this 1/2. So just for convenience, we're going to put a 1/2 here. But it doesn't change anything, because in practice, alpha can be any constant. So if you multiply by 1/2, 1/2 times any constant is still like any constant. So here, alpha characterizes step sizes. It represents how fast the various parameters are altered or modified. And here, nabla, this nabla sign or gradient sign, it's the gradient of the objective function here with respect to each component in the vector W. Okay, so differentiation, first element of the gradient is differentiated with respect to W1, second element with respect to W2, until the last element, which is the partial differential of the objective function with respect to the last W. Okay, so let's recall that our objective function here is the mean square error. So it's the expectation under the distribution mu, the long-term percentage of time spent in each state of the squared difference between the true value function and the approximate value function when here S has the distribution mu. Okay, so this is where we're trying to minimize the mean square error of the approximation of the value function. Okay, so of course we're trying to minimize this, but this quantity, the objective function on each point, it's unknown. So typically whenever we find ST, we have no clue what that value is. So why don't we know that? It's because this objective function depends on the true value function, and of course the true value function is unknown. So what can we do? Well, we can do something similar than what we've done in previous chapters. So when we apply a stochastic gradient descent method, then it entails replacing the gradient by an unbiased estimator of the gradient. Well, hopefully unbiased. If we cannot have an unbiased, at least some estimate of the gradient itself. So the estimate of the gradient is kind of a noisy version of the gradient. So here what we could do, instead of using the expectation in our update rule, if we want an unbiased estimate of the expectation, we can simply take what's inside the expectation, which is the square difference between the value of a state and its approximated value. So if we did that, if we replace the gradient descent by a stochastic gradient descent, where we replace the objective function by an unbiased estimate or some noisy estimate of this objective function, then what we would have would be the following rule. Okay, so we have that the next value of parameters is the previous value minus 1/2 times the learning rate times nabla, and here we replace the objective function by what's inside the expectation, which is the square difference between the true value function and its approximation. And when we calculate the gradient of this square here, well, when we have something to the power 2, the 2 goes in front of the bracket, which simplifies with the 1/2, and then we have to compute the derivative of the interior, which is derivative of our approximation of the value function with respect to W. Okay, so this rule, well, okay. If we truly observe the value function in ST on every time step, we could use that rule because here this quantity would be known. But in practice, of course, using this directly, it's impossible because this quantity is unknown. Okay, we don't know the value function in each state. Okay, but if we knew it, then this approach would attempt reducing the mean square error every time a new training example, ST and its associated value function, would be encountered. Okay. So again, a stochastic gradient descent. Why do we call it this way? It's because, well, it's a gradient descent because on every time step we move the parameters in the inverse direction of the gradient so as to reduce the the value of the objective function as much as possible. Okay, so here we're in fact we're taking a very small step for W in the direction where the square error that we've encountered decreases the fastest. Okay, so if we have an infinitesimal size time step, then we know the gradient points in the, or the minus the gradient points in the direction where the value function decreases the fastest. And here, why stochastic gradient descent? The word stochastic means that we don't have the true gradient, so we replace the gradient by a noisy estimate of the gradient, where in the presented case, the noisy estimate is simply one single instance of the random variable within the expectation. So the gradient, we don't have the true gradient of the objective function in our algorithm, we only approximate it. So it's not sure that on every time step the value function will decrease, okay, because we only have an approximation of the gradient, we don't have its true value. So it's possible that the approximation can be widely wrong, and in some steps it might increase the value function, the objective function instead of decreasing it. But in average, because the gradient estimate we have is unbiased in our case, then in average this procedure should tend to decrease the value function. So now there was this parameter alpha which represented the time step. So why alpha is typically small. So why do we consider small steps instead of large steps? So you could think, well, the bigger steps, well, it's better because we're going to optimize faster. So this should be preferable. But the reason why this isn't the case is because first, the value function, when moving the parameters in the direction of the gradient, assuming the true gradient was known, it would only be guaranteed to reduce the value function for infinitesimal size time steps. Okay, so if you take bigger steps, then you might not reduce the objective function, you might increase it. So it's important to take small enough steps so that you still retain your guarantee of reducing the objective function by stepping in the direction of the inverse or minus the gradient. Furthermore, one issue that we've discussed in the previous lecture, now the vector parameter vector W, it impacts not only one state at a time, but it impacts many states at a time. Okay, so here, let's go back to the update rule. When we apply this update rule, we shall move the parameters so that in a direction which is such that our approximation of the value function for state st will become closer to the true value function in st. But what about other states? So other states than st, what about them? And then because we're moving w, we also impact the estimate of the other states. So even if for state st, the approximated value function becomes closer to the true value function, then for all other states we have no such guarantee. So it might decrease the quality of the approximation for other states. Okay, so because of that feature, it's not necessarily good to have too large of a step every time, because even if you improve the situation for one state, you might have adverse impacts on the approximation of other states when you move W. So you might not want to move it too much at a time. Okay, so now stochastic gradient descent. Do we have convergence to the optimal approximation under this procedure? Well, in some specific cases, you have theoretical guarantees to converge to at least a local optimum. Maybe not the global one, this is not guaranteed, but to a local optimum, you can have some theoretical guarantees which typically entail first that you decrease alpha suitably through time. So in chapter 2, there were an example of such a set of conditions where the sum of alphas had to be infinity, but the sum of squared alphas had to be finite. So if you apply these conditions, then you typically have a guarantee of convergence to the optimal approximation of the value function. Okay, and also in practice, to have that, you need an unbiased estimate of the gradient to ensure such convergence. But in the previous algorithm we showed, our approximation of the gradient was unbiased. Okay, so in the previous algorithm, our approximation was unbiased, but in practice, it's infeasible because the true value function is unknown. So what do we do? How do we circumvent this issue? Well, we can still keep the previous update rule, but here in the value function with respect to st, of course, in practice, this is not known, so we have to replace it with something else. So once again, we shall replace the true value function by something whose expectation should be close to it. Okay, so ideally, we'd like to have an unbiased estimate of the value function, unbiased noisy estimate, but sometimes if we have no unbiased estimate, we might have some slightly biased estimate, but whose expectation it shouldn't be too far away from the true value function. Okay, so in the previous algorithm, we shall replace v pi st, which we do not know, by a target ut, which is some noisy version of the value function. Okay, so it's basically something that will estimate the value function and in which, on average, should not be too far from the value function. So if we do that, then the previous update rule becomes the following. Next estimate is the previous estimate plus alpha, the learning rate, times the target minus the approximated value function times the gradient of the value function, okay, or the approximation of the value function. So what are suitable values for ut, the target? Well, ideally, as we said, we would have an unbiased estimate of the value function, because if we have an unbiased estimate, then we have a guarantee of convergence. Okay, so if we have that the expected value of the target, given we're in state S, is the true value function, then we have guarantees of convergence. So this is great. So what are examples of this? If you use the target being the return starting in at time t, as in the Monte Carlo algorithms from chapter 5, then we have unbiased targets because we know that the conditional expectation of the return is the value function. So in that case, we do have an unbiased estimate. Okay, so mu could be the return starting on state t or time t. Okay, but as we mentioned, sometimes computing the full return takes too much time. So updating the states might be very long, and furthermore, the return might have a lot of variability, high variance. So this might slow down the learning, or make the learning like a bit noisy before reaching to more stable values. So we could replace the unbiased estimate by other biased estimates which have lower variance. So examples of things we could use for mu are the targets for other reinforcement learning algorithms. Okay, so for example, you could use the TD0 target, which is the next reward, plus the discount factor times the estimated value function at the next step. Okay, but here the estimated value function does rely on the current estimate of the value function. And or you, so this is the TD0 target. You could have the n step TD target. So once again, the expected value of the n step target, so the sum of the next n discounted reward, plus the bootstrapping term, so gamma to the power n times the estimated value function in n step. So this, for n sufficiently large, the bias is quite small, so you might consider this as a suitable target to plug within the previous update rule. Or if you have knowledge of transition probabilities, so for some problems we do have them, then you could replace the use the target as the expected value over all possible next actions, next states, and next rewards of the next reward plus gamma times the approximated value function in the next step. So this would be the target, which would be used in a dynamic programming framework where we do know the transition probabilities, and hope to do that. Typically, this summation should not be too large. Okay, of course, if this summation is too large, you can have some random sampling over actions and next states, but again, this is something possible. But for what we will do in this course, we'll typically focus on traditional like reinforcement learning targets, which are these ones. Okay, so we won't rely on transition probabilities, which are often unknown for many reinforcement problems. However, if we use these targets UT instead of the return itself, these targets, they all rely on an approximation of the value function, and this approximation, of course, it's not always exactly correct. So because of this approximation, typically these targets are biased in the sense that their expected value is not exactly equal to the value function vpi evaluated in the current state st. Okay, so because of this bias, we typically don't have the same theoretical guarantees of converging towards the optimal set of W, which minimize our objective function VE bar. Okay, so even if we use the targets in the last slide, which were biased, although we might not have an explicit guarantee of convergence to a local optimum for W, they can still be useful. Okay, so although we don't know exactly that they will converge to the minimum, they might still be useful and converging to some value which is not too far from the minimum and which might be sufficiently good for practical purposes. Okay, so although they might not lead exactly to the minimum, they might lead close to the minimum and lead to a point with sufficient performance. And furthermore, the bias targets from the previous slide, they're typically faster to compute because you don't need to wait for the end of the episode. Also, they have smaller variance. So because of that, they typically enable faster learning in practice, which is desirable. So all these approaches where we replace vpi st in the update algorithm by ut, which is a target, and then if we go back one slide, and then where the target depends also on the approximated value function, these are known as semi-gradient methods. So why semi-gradient? Let's discuss that. So why aren't they simply stochastic gradient methods? Why do we call them semi-gradient methods? So semi-gradient methods are similar to the stochastic gradient descent methods we've considered, but they disregard the dependence on the target with respect to W. Okay, so in previous slides, when we derived our update formula, we had somewhere in the update formula v pi st. Okay, so this v pi st was in the update formula. We said in practice we don't know it, but we still first derived the equations for the gradient descent, stochastic gradient descent with this quantity. But this quantity, if you differentiate it with respect to w, then this clearly doesn't depend on w, so this is equal to 0. However, in subsequent versions of the algorithm, we said we're going to replace this v pi by mu t, and now the derivative with respect, okay, let's write it like this. The derivative with respect to mu t, with respect to parameters of mu t, it might not be 0, okay, because, so if we have mu t being the return itself, then this would be 0, but if ut, as in the previous slide where we use targets who depend on the approximated value function, then this might be different from 0. Okay, so for example, if we recall we used the TD0 target, then ut is RT plus 1 plus gamma times here st, sorry, I don't write really well, and here wt. So we see that if we use, for example, the TD0 target for ut, then the target depends on the estimate of the value function on the next state. So the partial derivative of ut with respect to the parameters is typically different from 0. Okay? So why do we call the previous methods where we replace v pi by ut semi-gradient descent? It's because we use the same formula than gradient descent. We replace v pi by ut, but what we do is we disregard the fact that this partial derivative is not 0 in practice. We're going to use the same previous formula, which assumed that this derivative was equal to 0. So let's maybe illustrate that better. The explanations are right in this slide. So assuming we would do a stochastic gradient descent with the target mu t, then we would have the following update rule. Okay, so the next estimate would be the previous one minus 1/2 learning rate times the gradient. So this is kind of the interior of our objective function within the expectation. So this is a stochastic gradient method, but where we replace the true value function by the target. So if we applied that, then we would differentiate the square with respect to the various parameters in W. So if we do that, then we apply differentiation, then this becomes equal to this. The 2 goes in front, cancels out, and then we have the derivative of the interior, which is the gradient of ut minus the gradient of v pi. Okay, so here it's flipped. It's gradient of v pi minus gradient of u. But so the order is flipped because we flipped the sign here. Okay, so we flip the sign here, minus to a plus, and we flip the sign here. So if we would be rigorous about updating the parameters, then there would be this term here, the gradient of mu t, the target with respect to the weights, which would appear here. But, so this would be the stochastic gradient method. But now, since we disregard this guy, if we do disregard this guy, we obtain the following equation here. So if we just suppress this guy, we obtain this. And this is exactly of the form of the previous gradient descent we've obtained, except we replace the true value function here by the target mu. Okay, so we can see we call it a semi-gradient descent because it's as if we did a gradient descent, but we did not take into consideration this this portion of the gradient here, which is the gradient of the target with respect to W. So this is why we call it semi-gradient descent. Okay. So here, okay, so this is the semi-gradient method. This is what we're going to use pretty much for the rest of this chapter, okay, and even in subsequent chapters. Okay, so, well, not all, but let's say chapter 11, we're going to rely on this. Okay, so semi-gradient methods is what we're going to propose in this course to update the parameters of our approximation of the value function in the context of the presence of approximation. So here, this is the generic semi-gradient descent rule, but in the next slide, we're going to give a specific example where we can replace here the target mu by the TD0 target. So if we do that, we have the following. So u, if it's the TD0 target, the next reward plus the discount factor times the estimated value function at the next state. Then in the semi-gradient update rule, we have the following. So the next value of parameters is the previous value plus the learning rate times this is the target, TD0 target, minus the current approximated value of the value function times the gradient of the estimated value function in SW. Okay, so if we want to make a parallel, this I haven't written it in the slides, but it's still nice to talk about this. If we want to have a parallel before with what we did earlier, so in earlier chapters, the update rule for the value function was something like next estimate is equal to previous estimate. And estimates of what? In the previous chapter, the estimates were directly estimates of V pi st. Okay, so we had something like next estimate is previous estimate plus the learning rate times the target minus the previous estimate. Okay, so this is what we had in previous chapters. So now if we look at what we have in the current chapter, well, first, instead of estimating the VPIs, we estimate the parameters driving the approximation. So it's not estimate of VPI itself, it's estimates of the parameters. But what we have here is still with a similar form. So the next estimate is the previous estimate plus a learning rate times the target minus the current estimate of the value function. But so here this is an estimate of parameters. This is an estimate of the value function. And here what's new here is that we have this gradient here that appears, which wasn't there in the previous types of formula. So the gradient appears here, and why do we have this term? What's the interpretation of this? You can kind of explain it through the following way. It's because these represent, okay, maybe I'll use a different color. They represent errors on the value function. Okay, so this is in value function units, whereas this here, it's in parameters units. So the gradient with respect to the value function it's kind of a term which translates units of value function into units of parameters. So it tells you, it's kind of a translation. If you want to move the value function by this much, then you should move the parameters by this much. So it's kind of the ratio of the variation of the value function into variation of parameters. So this term here, it acts like so you can see it as a translator, which translates variations of value function or errors of value function into variation of parameters. So this is I think it's a nice way to uh, characterize this new gradient term, which wasn't there before. Okay, so before it wasn't there because here these estimates, here and here, both were in units of value function because you estimated value function, and this error here was in terms of value function itself. So you didn't need this gradient term before to translate units of value functions into units of parameters. So this is why we have this new gradient term here. All right, so this completes the current video. I'll see you in the subsequent video to describe the various approximation functions that are proposed by the textbook. Okay, so here we said in the two previous lectures, we said we rely on v pi hat, which is some approximation of the value function, some parametric approximation, and we said these parametric approximations can be many things, maybe linear functions, neural networks, etc. Now we will discuss more specific examples in subsequent lectures. So have a nice day and take care.